Hi dear students, welcome to today's online class. Today we will discuss about an important concept in NMR spectroscopy that is called chemical shift. In the previous class we have learned that due to the secondary magnetic field generated by the circulating electrons around the nucleus of the proton will reduce the applied field, or it will shield the applied magnetic field, so that different protons in a molecule will absorb at different frequency, radio frequency, giving different signals in NMR. If all the protons in an organic molecule is feeling the same applied field, it would have given only one NMR signal, but it is not so. We can see different peaks in the NMR spectrum of a molecule. It is because of this phenomena of secondary magnetic field generated by the circulating electron. If the secondary magnetic field is more, that means there is more shielding, then the proton will feel a lower applied field, and we know that nu is proportional to B0. Lower the field, lower the frequency. If the secondary field generated is less, weaker, then the proton will experience a higher applied field. Higher the field, higher the frequency. That way, different sets of proton in a molecule which are in different chemical environment give rise to different NMR signals. See, in this molecule chloroethane, you can see that chlorine is highly electronegative, withdraw electrons towards it by inductive effect, minus effect. So, electron density around CH2 will be much lower than that around CH3. So here, secondary field generated will be lower because electron density is less, and here it will be more. So when the secondary field is less, this will feel more applied field and it will absorb at a higher frequency. Here there is more shielding because more electron density around this CH3. So more shielding by secondary field. So the applied field felt by this CH3 proton will be less, and frequency of NMR peak will be less. So this is a basis of chemical shift. Now, what is chemical shift? How we represent this? That's a question. See, in the equation for frequency, we have seen that this equation nu equal Gn beta n B0 by h. This is for an isolated proton. So chemical shift actually means the separation or the difference in absorption position of a particular proton which is present in a particular chemical environment compared to the isolated proton. So compared to an isolated proton which is having no electrons around, which is not possible, what is the absorption frequency of the given proton? That difference is called chemical shift. Shift in absorption position of a given set of proton compared to an isolated proton. The absolute chemical shift cannot be determined because we cannot have an isolated proton. So what to do? There, as usually in science, we will go for a relative scale, right? So here, we make use of a reference compound that is called TMS, tetramethylsilane. TMS, tetramethylsilane. This is used as a second is a reference compound for determining chemical shift. The structure, it is simple. It's a tetrahedral molecule, tetramethylsilane, 4 methyl groups, silicon at the center. Now the chemical shift of this TMS is arbitrarily fixed as 0, and all other protons in organic molecules are compared to this. Now, see, when in a molecule, in an organic molecule, due to various functional groups, there can be, as I said, there is diamagnetic shielding by the secondary field produced by the circulating electron. That's called shielding. If there is an electronegative atom which withdraw the electron density and reduce the secondary field, then it is known as deshielding, correct? Shielding generally by the secondary field produced by the circulating electrons, and if there are some factors which reduce the electron density around the proton, then we call it deshielding. So due to shielding and deshielding, different protons, different sets of protons in a molecule absorb at different frequency because they feel different applied magnetic field strength. Now, what makes TMS a good reference compound? TMS is called a reference secondary standard. It's a secondary reference compound because we are taking it for a relative purpose. Advantages of TMS is that, one, that it is chemically not reactive. See, when we carry out NMR technique, we will make a solution of the compound to be analyzed. So we will have a solvent, okay, and we will put the compound in it, and also we will add a pinch of TMS for this chemical shift purpose, a little bit of TMS. So this TMS should not react with the compound or the solvent, so it's chemically very unreactive. That is a positive factor. Secondly, its boiling point is very low, 27 degrees Celsius, so it's reasonably volatile. So after the technique, you can remove TMS from this mixture, from this sample easily, and recover your valuable sample. See, we will have some very costly samples which is used for taking the NMR, and we may need it again. So TMS can be easily removed from this. And another thing is that TMS is miscible with all the solvents. It is miscible, so you can make the solution easily. And another point is, very important point, is that TMS has 12 protons which are chemically equivalent, correct? See, how many signal will be given by this TMS in NMR spectrum? Only one, because all these are identical. If this is labeled as A, this is also, these are all having same conductivity, same chemical environment. So there are 12 protons. Okay, so that will give a very intense peak. Intensity of NMR peak is proportional to the number of protons in a given set. So this gives a very intense peak in NMR. And finally, another thing is that this is most shielded proton, because silicon is not electronegative, So these protons are highly shielded, so that all other protons, all other organic protons present in various organic molecules in various functional groups will absorb at a frequency which is higher than TMS. So it's convenient to draw the spectrum. The scaling will be quite convenient. Due to these reasons, TMS is used as a very good reference compound or as a secondary standard. Now, how we represent this chemical shift value? What is the equation for this? So, we redefine chemical shift now on the basis of the secondary standard or TMS as chemical shift indicate the shift in absorption position of a particular proton compared to the reference compound, that is TMS. With respect to TMS, how much is your proton absorbing at what frequency? Okay, now representing chemical shift value. How we represent chemical shift value? Earlier, the symbol used for chemical shift was tau, and now it is del. This is represented, used now, and now chemical shift del is defined as frequency of the sample or your compound minus frequency of reference compound, that's TMS, by frequency of reference into 10 raised to 6. Why 10 raised to 6? Because chemical shift is expressed in ppm. So to convert it into ppm, we multiply by 10 raised to 6, because this value will be very, very small. So to make it a reasonable figure, we change it into ppm. So frequency at which the given proton is absorbing, that is new sample, frequency of the TMS, absorption of TMS, and this is again frequency of absorption of TMS. You get this chemical shift value. Now for TMS, okay, for TMS, what is del value? It is arbitrarily fixed as I said, 0. Between del and tau, the relation is dou is equal to 10 minus tau. So what about the tau value of TMS? Tau value will be, it is 10. Okay, right. But in modern literature, we represent chemical shift using del only. So remember that. Now, coming to next, what are the factors affecting chemical shift? Okay, mainly there are 4 factors affecting chemical shift. Number 1, as we have learned at the beginning, it is the secondary magnetic field generated by the circulating electron which is responsible for this chemical shift, right? So that is what is called diamagnetic shielding. So what is diamagnetic shielding? Basically, this is the reason for chemical shift. Diamagnetic shielding by the circulating electron. More the shielding, lesser will be the field experienced by the proton, and lower will be the frequency of absorption. Lower the shielding, greater the field experience, greater the frequency. Now the second factor is deshielding. There can be some deshielding by electron withdrawing groups. Okay, deshielding by electron withdrawing groups. That is, as I said earlier, for example, if you take CH2Cl for example, this chlorine being highly electronegative and it is minus I group, withdraws electron, right, towards it. So what happens to electron density around methyl? It will reduce. This is known as deshielding, because it is reducing the circulating electron around it and reducing the secondary field generated. So it's a kind of deshielding. So groups like Cl, NO2, all minus I group, all electron withdrawing groups will reduce the chemical shift value, or it will it will reduce the electron density, okay, and it will cause what is called deshielding. So when this deshielding, electron density decreases around here, it will feel a higher applied field and frequency will be higher, del value will be higher. Remember that. Now the third factor is an important factor, that is called magnetic anisotropy. Magnetic anisotropy. What is this? It's a very important thing. You know, anisotropy is a property of having different magnitude for a given quantity in different direction. Okay? If there is different magnitude for a given property in different direction, that's called anisotropy. What is magnetic anisotropy? See, in pi systems, this is applicable to pi system. That means organic molecules having pi electrons. Let's take for example benzene. Okay. See, in benzene you know that there are alternate pi bonds and there is complete cyclic conjugation, and due to this pi electron density appear as a ring, you know that. So there is a circulating pi electron here above and below the plane of the ring. Now this pi electron, circulating pi electron, will definitely produce a very good secondary magnetic field, and it will have this kind of direction for the magnetic flux lines as usual. And interestingly, it is that the hydrogen atoms on benzene ring, you have 6 hydrogen atoms. If you are applying, the applied field is here, okay, and this is the direction of the secondary field, correct? So it is in a shielding mode around here, but when it comes to this ring hydrogen, see that this secondary magnetic field produce these now in the same direction as the applied field. So when the direction changes, its nature is changing. Here it is what? It is deshielding. Here it is shielding, but there is no proton here. Okay, here it is deshielding. If we represent it like using some signs, we put it is positive zone here and it is negative zone here. So all the, when it comes, all around, that all the protons will be getting deshielded. So when there is deshielding, it will absorb at a higher frequency. Generally, ring protons absorb at 6 to 9 del value is 6 to 9, very high value. If you find peaks around 6 to 9, you can understand that the compound is aromatic. Okay, a similar thing happens so this is called magnetic anisotropy. Deshielding, shielding and deshielding experienced due to the different due to the pi electron ring, the secondary field generated by the pi electrons, and which depend on direction. Similar is the case of aldehyde group. See, aldehyde group has at sp2 hybridization, right? Okay, suppose this is, or let me write H here for convenience. Now this pi electron will have similarly will have the secondary field, and this one also is having deshielding in the same direction as applied field. So what happens? This proton will feel a greater field than applied, correct? A greater field than applied. So higher field and higher frequency. See, aldehyde is having a value of a quite high value, around it comes to around 9 to 11 del value. It is because of this magnetic anisotropy. Same thing happens in the case of alkenes. See, in the case of alkene also, same thing happens. See, if there is a vinylic proton, for example, let me show one proton here. This also will have a secondary field, which when come to this proton, when it comes to the proton, it is in the same direction as the applied field. So alkene is also, vinylic proton is also having higher del value. The value comes to around 2 to 4, something like that. So all these are cases of deshielding due to the pi electron ring current and the secondary field produced by the pi electron ring current, and this is magnetic anisotropy. But so here these are all shielding, deshielding, right? Frequency is increasing. The secondary field produced due to the pi electron ring is in the same direction as the applied field, and it is giving a greater effective field for the protons, and frequency is higher. But there are cases where there is deshielding happens. That means in some direction it is leading to deshielding. An example is the case of acetylene. See, it's contrary to these cases. What about acetylene? See, acetylene, it's a linear molecule. Okay, this is acetylene, and see this, that it has two pi bonds, and the pi bonds are formed. If you represent the pi lobes, it is all around, correct? You will have a cylindrical kind of electron density here, and this is the direction of the secondary field produced, correct? Now compared to the applied field, how about the secondary field? For this proton, acetylenic proton, see that it is opposing the applied field. For this one also, it's coming like this, opposing. So what is this called? This is shielding. So for acetylenic proton, the secondary field produced by the pi system or the pi electron is shielding. Whereas in the case of all these alkenes or alkenes, similarly aldehyde and benzene or aromatic system, the secondary field produced is deshielding. Here it is shielding. That's why this phenomena is called magnetic anisotropy. However, this factor will make the chemical shift for various types of protons quite different, and we get very distinguishing peaks in NMR. Or looking at the chemical shift value, you can guess about the type of proton present in your molecule. See, in the case of acetylene, the del value is found to be it is found to be at around 1.5 to 2.5, whereas in the case of acetylene, it was, as I said, it is something around 4 to 5 actually, 4 to 5. So this is actually lower value compared to this alkene. Acetylene is lower because of the shielding. Even though there is one more pi bond in acetylene, but it is producing a kind of shielding and frequency is lower. Okay. Now finally, the fourth factor is hydrogen bonding. Okay. Hydrogen bonding will cause a little bit of deshielding, like in the case of alcohol, etc. See, when there is hydrogen bonding, okay, so the electron density will lower around this hydrogen, this bond will get weakened and electron density decreases, and what happens is that this will have a slight deshielding, and deshielding will lead to a little greater frequency for NMR peak. So these are various factors affecting chemical shift.